Alright guys, how is everybody? Today we're going to deal with some mass defect stuff and binding energy. That's our plan for today. Alright, so a little bit of math. Alright, so when we're dealing with mass defect, right, a bunch of things that we should just run through here. Now, in general, the energy released during a nuclear reaction is usually much greater than during a chemical reaction. Oops. So in a chemical reaction, we're switching those electrons, potential energy changes a little bit, and some energies will be given off or absorbed. When we're talking about nuclear reactions, we're converting a small amount of mass to energy, and we get huge amounts of energy in nuclear reactions compared to chemical reactions. The nuclear force binding protons and neutrons is much greater than the Coulombic forces binding electrons to the nucleus. Right, so we have this nuclear force called the strong force that hold these protons and neutrons together in the nucleus. Okay, that force is much stronger than this Coulombic force between the nucleus and the electrons. So that nucleus is positively charged, the electrons are negatively charged, so we have that attractive force. That's very weak compared to this nuclear force. Changing the number of protons and neutrons in the nucleus, or in a nucleus, involves much larger energies than changing the location of an electron. Alright, well, what dictates, or what is the relationship that dictates the amount of energy that's released in a nuclear reaction? Well, it's that famous equation of E equals mc squared. Okay, so this is Einstein's equation. It's the relationship between energy and mass. Okay, so this stands for energy, this is mass in kilograms. C stands for the speed of light. Which is 2.9979 times 10 to the 8th meters per second. So we can use this equation to help us figure out how much energy is evolved during a nuclear equation. So in a nuclear equation, or in a nuclear reaction, mass is not completely conserved. A small amount of mass is converted to energy. Well, how much energy comes out? Well, you have to figure out how much mass is lost. The difference in mass between the products and reactants, which is the change in mass, delta M, is called mass defect. And delta M is equal to the mass of the products minus the mass of the reactants. Number 7. The change in mass, the change in energy of the nuclear reaction so a change in energy or a nuclear reaction is related to our change in mass. So we can change Einstein's equation a little bit. Delta E, or our change in energy, is equal to our change in mass times the speed of light squared. Right? And we'll be using this to figure out how much energy, or we could go the other way, how much mass, right, is converted. All right, so let's try to calculate the mass defect. Calculate mass defect in the following nuclear reaction. Uranium-238, which has an atomic number of 92, goes to thorium-234, which is 90, and 4,2He. Okay. Now, we need to know the mass of the nuclei. Well, uranium-238 has an atomic mass of 238.0003 AMUs. Thorium-234, its actual mass is 233.9942 AMUs. And helium, its exact mass is 4.0015 AMU. Right, so we look those up, we have them. So now our delta M is equal to the mass of the products minus the mass of the reactants. So we have to add these two, so we have 233.9942 plus 4.0015 minus our reactants, which are 238.0003, and we figure that out, it's a negative 0.0046 AMUs. Right, so this is if we have one. Okay, if we have one atom of uranium going to one atom of thorium to one alpha particle. All right, so we lose 0.0046 AMUs. All right, this is in if we had one atom. Well, what if we have 1 mole? Well, if we have 1 mole of uranium, we would lose 0.0046 grams. Okay, that would be our mass defect. So where is that going? Well, that mass is actually turned into energy, and we can calculate the amount of energy. So let's try this. What is the energy change per mole of this reaction? Oops. Well, delta E equals delta M times the speed of light. We're trying to find delta E. Right now, the mass has to be in kilograms, so we're going to have to convert to kilograms. All right. Now, why does it have to be in kilograms? Well, it's how a joule is defined. A joule is defined as a kilogram dot meter squared over second squared. This is what's equal to a joule. Okay. So we have to convert this, and we can do it right in the equation. So I'm going to say, well, our mass is negative 0.0046 grams. Put the conversion in. 1,000 grams is 1 kilogram. And then we take the speed of light, which is 2.9979 times 10 to the 8th meters per second. And we're going to square that whole thing. When we do all this math, we end up with a negative 4.1 times 10 to the 11th joules, or kilogram meter squared second squared. Right, now the negative means that the energy is given off. Okay. Look how much energy that is. So just by converting this tiny, tiny small amount of mass in a mole, all right, this is how much energy we would get out from that mole. That's a huge amount of energy. That's why we have these nuclear power plants. They produce so much energy with such a small mass loss. There's a little twist that we have to put on here, and we'll do it by using a problem. Calculate the mass defect and energy change in the formation of 1 mole of oxygen 16 from its component parts. In other words, let's put together oxygen 16 from the original neutrons and protons. So we're producing oxygen 16. Right, so how many protons do we need? Well, we need 8 of them. Okay, and we also need 8 neutrons. Okay. So to put together oxygen 16, we need 8 hydrogens, 8 neutrons, 8 protons, which is really just a hydrogen nucleus, 8 neutrons, and that comes together to form our oxygen. All right, so just remember that this is a proton. Well, we need the masses of hydrogen, nitrogen, and the oxygen 16. Okay, and you can look up, okay, you'll be given these numbers, or they're in the textbook. All right, so a neutron is equal to 1.0086649116 AMUs. A proton is 1.007276466 AMUs. And oxygen 16's mass is 15.9994 AMUs. Well, now we can just do our change in mass. Our change in mass, not change in energy, is equal to the mass of our products times the mass of our, minus the mass of our reactants. So our delta M is equal to our products, which is our oxygen, 15.9994 AMU, minus our products. All right, now we have, let's do this. So we have 8 protons, so we're going to have to multiply 8 times 1.007276466 plus we have 8 neutrons. 8 times 1.008664916 AMUs. $15.9994 AMUs minus 16.12753106 AMUs. So our change in mass ends up being negative 0.1281 AMUs. This is how much energy is released as we go from our individual atoms into oxygen 16. All right, now this is creating 1 atom of oxygen 16. I want to know for 1 mole. So for 1 mole, it would give off a negative 0.1281 grams in 1 mole. Okay, so this is our mass defect. Well, how much energy would that be? Well, our change in energy equals our change in mass times the speed of light squared. Okay. So we got negative 0.1281 grams. We have to convert that to kilograms. So we got 1,000 grams, 1 kilogram. Oops, why I put that there? It should be there. Times our speed of light, which is 2.9979 times 10 to the 8th meters per second squared. It would give off 1.151 times 10 to the 13th joules, which is, again, a ton of energy. That's why we use these nuclear equations, okay, because they produce so much energy. All right. This goes right along with binding energy. So our binding energy is the energy that holds the nucleus together. That binding energy generally increases as the atomic number increases, because more energy is needed to hold the nucleus together. Right? So the bigger the atom, the more protons and neutrons we have, the bigger the binding energy. All right? The more energy we need to hold that nucleus together. Now, eventually they get so big that they won't stay together. They'll immediately fall apart. All right? There is no energy there is not enough energy to hold those nuclei together. The larger the binding energy per nucleon, the more stable the nucleus. Okay, so we're going to be looking at per nucleon, per proton and neutron. Right, that's what we're going to be looking at in our binding energy. And what I want to do is, since we just worked with oxygen a minute ago, oxygen 16, let's go ahead and use that. Okay, so let's use the formation of oxygen 16 to talk about binding energy. So our mass defect, okay, was equal to a negative 0.1281, and that was grams per mole. Okay, and then when we calculated our change in energy, it was equal to a negative 1.151 times 10 to the 13th, and that was again joules per mole. Now we're going to be using this energy, right? Because this is the energy that's actually going to be used. It's used to bind that nucleus. All right. So binding energy is usually represented as energy released per nucleon. Remember, that's the protons and neutrons. Well, so we need to do some conversions here. First thing we're going to do is we're going to convert to per oxygen 16 nucleus, because this energy is per mole, so we need per nucleus to start with. So we're going to start with that energy of negative 1.151 times 10 to the 13th joules per mole. All right, and we're going to use Avogadro's number. For every 1 mole, we have 6.022 times 10 to the 23rd nuclei. So that means we have negative 1.9113 times 10 to the minus 11th joules per nucleus. Well, we need per nucleon. So now we're going to convert that to per nucleon. Well, in oxygen 16, there are 16 nucleons. 8 protons, 8 neutrons. Right? So we take our per nucleus, negative 1.9113 times 10 to the minus 11th joules per nucleus. For every 1 nucleus, we have 16 nucleons. So when we do that math, we get negative 1.1946 times 10 to the minus 12th joules per nucleon. All right. So I'm going to write that right here. So this is how much energy that would be released per nucleon as oxygen 16 forms. Well, if this is how much is released when it forms to form that nucleus, that's how much energy would have to be absorbed to break it apart. So that means positive 1.1946 times 10 to the minus 12th joules per nucleon, or joules, would need to be absorbed to decompose an atom of oxygen 16 into protons and neutrons. Okay? This is what's called our binding energy. All right, let's do one more problem. Let's calculate the binding energy for the formation a helium atom. Alright, so our helium atom is a 4,2He, that's what we're making. We need 2 protons, and we need 2 neutrons. They will come together to form this helium nucleus. Alright, well now we need those masses. So helium is equal to 4.0026 AMUs. Our proton is 1.007276,466 AMUs, and our neutron is 1.0086649,116 AMUs. So now we can do delta M equals the mass of our products minus the mass of our reactants. So our delta M equals 4.0026 AMUs, that's our product, minus 2 times 1.007276466 plus 2 times 1.0086649,116. So we end up with negative 0.02928 AMUs. Okay. Now, if we put this in grams per mole, right? So this is for 1 atom. Now we want a mole. Okay. Be negative 0.02